Hello to all physics enthusiasts and fans of physical experiments. This is Andrei Shetnikov, and today our discussion will be dedicated to the phenomenon of resonance, which is extremely important in both physics and engineering. And we will start this discussion with a very simple experiment. Here on my table, I have a mechanical vibrator powered by an alternating oscillation generator. And I will take this elastic ruler with two weights at the ends. I will set it up on this generator. Now we will connect it and see what happens to the ruler at different frequencies. We will observe carefully and see how it behaves when subjected to various conditions. And so we went ahead and turned on the generator, and the ruler began to oscillate in sync with it gradually. The current frequency is approximately 8.4 Hertz, and we will be gradually increasing it further. And we see that the amplitude of the ruler's oscillations gradually becomes larger and larger over time in a gradual manner. For the image, we need to take into consideration the stroboscopic effect, which unfortunately cannot be eliminated. 8.99 Hertz and the amplitude became quite large. Could it continue to increase as the frequency rises? But no, the frequency is increasing, 9.4 Hertz, and the amplitude has decreased. Let's wait a little longer, 9.6 Hertz, 7 Hertz, and the amplitude has become quite small, 9.6. During the 70s, and the amplitude became significantly very small indeed. What exactly is this frequency of 9 Hertz at which the ruler's response was maximal? Answering this question is very simple. For this, without turning on the generator, I will make the ruler oscillate. And we see that it oscillates as we observe this phenomenon clearly, damping at a frequency of exactly 9 Hertz. And now we can define resonance. Resonance is the phenomenon of a sharp increase in the amplitude of oscillations when the frequency of the external forcing oscillations approaches the natural frequency of the system's own oscillations. And it is clear that the phenomenon of resonance needs to be thoroughly understood and well comprehended in order to fully grasp its implications, because it has the potential to bring about both significant benefits and equally significant harm, affecting various aspects of life in profound ways. When your refrigerator or washing machine and other appliances begins to rattle due to resonance, it causes a lot of inconvenience, such as noise and vibration. But undoubtedly, all of you have, that is to say, been informed about the disaster that took place in France in 1850, when an entire battalion of soldiers was marching in step across a bridge, and the bridge went into resonance with their march, collapsed, and in total, approximately more than 200 people died. In our next experiments, we will be conducting more precise and additional measurements. And for this, we have assembled this setup. The foundation of this device is a pendulum that is carefully mounted on a rotation sensor, which allows for precise and accurate measurements. We adjusted the length of this pendulum so that its period is exactly 1 second. Accordingly, it is now oscillating at a frequency of 1 Hertz. And at the bottom of this pendulum, a small but powerful permanent magnet is attached, and we will swing it back and forth using two precisely positioned electromagnets through which a carefully controlled alternating electric current will be passed. And first, initially we will administer a constant voltage of 15 volts to these electromagnets. The pendulum is pushed to a 1-degree deviation, and then it very slowly oscillates and gradually settles at a half-degree deviation, and eventually. Now we will swing the pendulum with an amplitude of only 2 volts, but with a variable voltage at the pendulum's natural frequency of 1 Hertz, which is the natural frequency of the pendulum. And we can see that from such weak pushes, the amplitude of the pendulum gradually becomes larger and larger, which is clearly visible on the graph of the angle versus time. And if you just wait a bit longer, the pendulum will swing to an amplitude of approximately 30 degrees. And yet, the amplitude of the voltage we are applying, which is 2V, is much less than the 15V of direct current voltage used in the first experiment with this setup, showing a significant reduction by a significant margin. So, resonance works in a way that very effectively and swings the pendulum to really extremely large amplitudes. What will happen if we move slightly away from resonance and drive this pendulum with a periodic force at a frequency somewhat different from its natural frequency? It turns out that the result of such an experiment will significantly depend on how quickly the damping of the pendulum occurs. Here we have, as you can see, a very good bearing installed, so the damping does not occur quickly. Indeed. The pendulum reduces its amplitude by approximately 40% in about a minute, over 60 cycles. And to make this damping more noticeable, we will now slightly modify our experimental setup, slightly. And we will place a plate under the pendulum, which can be submerged to different depths in the water in order to provide varying degrees of damping. Now, we will proceed as follows. The plate is slightly submerged in the water for providing the following steps. I gently pull back the pendulum and carefully watch how its free oscillations damp. And I see that the amplitude of these oscillations has decreased by half over 18 periods. Now we will carefully focus on the forced oscillations of the pendulum. I will gradually apply an alternating voltage to the electromagnets, slowly changing it from a frequency of 0.9 Hz to a frequency of 1.1 Hz. And at the same time, I will observe how the amplitude of the pendulum's oscillations adjusts to the applied frequency. To ensure this adjustment is accurate, the entire experiment will be conducted over 20 minutes. The resulting curve, which is indeed commonly known as the amplitude-frequency characteristic, or the AFC of our device. At the resonance frequency, the amplitude of the pendulum's oscillations was 7.6 degrees. Now let's draw a horizontal line corresponding to half of the resonance amplitude of 3.8 degrees, a full 0.8 of a degree. This line intersected the frequency response graph at 2 points, and the frequency difference between them is 0.032 Hz. We will consider this value as the width of the resonance peak, which is a crucial parameter in our experiment. Now, I will push the plate a bit harder to observe the changes more clearly, and thereby increase the damping. What will happen to the resonance curve as a consequence of this? And we see that the peak resonance amplitude has become approximately 2.5 times lower, but the width of the resonance peak has become wider by the same factor. Let's increase the damping of the natural oscillations even more, and the peak amplitude became twice as low, while the width of the resonance peak became twice as wide. And it is basically very apparent why. Indeed, the lower the resistance of the medium, mostly resulting in greater amplitude to which pendulum swings at resonance frequency. The force acting on the magnet of the pendulum from the electromagnets is constant in amplitude and does not depend on the speed at which the pendulum swings. However, the resistance force of the medium increases with the speed of the pendulum, and at a certain characteristic speed, these two forces become equal in magnitude. Beyond this point, the pendulum will no longer swing because, at even greater amplitudes, the resistance would outweigh the driving force. We have discussed the amplitude-frequency characteristic of the pendulum at resonance, and now let's talk about how the phase of the pendulum's oscillations behaves. And for this, I'll conduct a simple experiment. I have the pendulum in my hand and need to find its natural frequency. 1, 2, 1, 2, 1, 2. Now I will try to move the pendulum with my hand more slowly, carefully, and gently. 1, 2, 1, 2, 1, 2. Keep repeating this rhythm steadily and consistently. And we see that the pendulum definitely swings undoubtedly in the same direction as the hand. Now I try to do it quickly. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And we see that the pendulum swings in the opposite direction to the hand. Well, that was harder to do. Now it needs to be done at the resonance frequency. We find it again. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. The pendulum swings very strongly while the hand movements are very weak. And it is better to perform this experiment on a real setup. And we will use our main setup once again because it conveniently allows us to record both the current in the coils, which is directly proportional to the force acting on the magnet, and the deviation of the pendulum from its neutral position. This setup is highly efficient and provides accurate measurements. This graph shows the oscillation at a frequency of 0.95 Hz, which is less than the natural frequency of the pendulum's oscillations. The blue sine wave represents the current in the electromagnets, and the red one represents the angle of the pendulum's deviation. And we see that the pendulum deviates in sync with the oscillations of the current. In this graph, the frequency of the driving force is approximately 1.05 Hz higher than the natural frequency of the pendulum. And we see that the current and the pendulum's deviation now oscillate in antiphase, just as it did in my simple experiment with the ball on a string. And finally, the third graph, where the driving frequency matches the natural frequency of the pendulum at 1 Hz. We see that now the oscillations of the current and the oscillations of the pendulum are phase shifted by 90 degrees, and the pendulum is pushed the hardest by the driving force when it passes the lowest position at the highest speed. And from this follows a very simple and useful piece of practical advice for you to follow. If you are swinging on a swing, it is best to push it not at the top, but at the bottom point, and it is clear why. The input power needs to be maximized, but power is essentially the product of force and speed, and indeed the speed of the swing is maximal when it passes the lowest point. It is important to understand a system can have not just one, but many natural frequencies of oscillation, which is often encountered in technical constructions. And at each of these specific and distinct frequencies, resonance oscillation phenomena can occur, which we will now demonstrate in detail using this setup, where a plastic hoop is securely and firmly attached to the oscillation generator device, and we will use the generator to oscillate it in a controlled, precise, and consistent manner. We started with a frequency of 7.5 Hz. So far, the amplitude of the hoop's oscillations is still small, but it is getting bigger and bigger. We are approaching the first resonance, 8.5 Hz. Look at just how much the hoop is oscillating. Definitely quite a bit more, 9 Hz. Then the frequency increases and the amplitude of the oscillations decreases. The first resonance has been passed. Now we start at a frequency of approximately 28 Hz, and we approach the second resonance. 4 nodes are clearly visible, not just 2 as the first time, with antinodes indeed between them. The frequency of 31 Hz is the maximum, and beyond that, the frequency increases while the amplitude of oscillations decreases, and the second resonance is passed after the first. And now we will look for the third resonance, specifically this time with 6 nodes and antinodes between them, in this case. And here we see that the amplitude keeps growing and growing. We are approaching a frequency of 67 Hz. This is the maximum amplitude, and the third resonance is found. It is clear that if we continue to increase the frequency, we will find the next resonance in the same way. We have talked sufficiently enough about the basic properties of mechanical resonance in detail and thoroughly for the first time. But of course, oscillations can definitely be of other types as well. Sound oscillations indeed correspond to acoustic resonance. Electrical oscillations correspond to electrical resonance. There are indeed also various other types of resonance, such as nuclear magnetic resonance, which is in fact used in magnetic resonance imaging as well. It is important to note that each of these individual topics is complex and detailed, and they each warrant their own separate and dedicated video. And now I return to our original setup, having removed the breaking plate, and in this sense to our original experiment, essentially, in essence, fundamentally, and importantly. And I will swing the pendulum at the resonance frequency, which is the natural frequency where the system oscillates with the greatest amplitude. But I will wait a bit longer and see what happens to the amplitude, which is the height of the oscillation when it reaches its peak values. And it certainly grew to a maximum value, but then for some unknown reason began to decrease. And almost exactly a minute later, it noticeably diminished, even though the electromagnets continued to drive the pendulum. And this alternating increase and decrease in amplitude happened over and over again. And for the amplitude of the oscillations to stop changing, you will indeed have to wait a very long time. The question is, why does this happen significantly? Share your thoughts on this in the comments section of this video on YouTube.